this is part 2 of chapter 8, continuing applicative functors and profunctors. In part 1, we looked at practical examples of applicative functors and profunctors and their use. In part 2, we concentrate on the theoretical properties of these functors. To begin, recall that applicative functors have the map2 operation, but also they have map3, map4, and so on. Do we need to define them separately for all n, mapN, which would be unfeasible perhaps, or can we have it in some other way? And the answer to that question leads us to an operation called app. Before we look at the properties of this operation, let's try to define mapN on a specific functor either of string A. So consider this type constructor, which is a functor in A. And let's try to define mapN and use it. And let's see if we can do something better than just doing mapN. Here is map2. It takes op of A, op of B. It also takes a function from AB to some z. So A, B, and z are arbitrary types, parameterized here. And we return op of z. So how do we do that? Well, for an either, that's a straightforward computation. We match. If there are two lefts, we use the monoid instance on string, where we just concatenate the two strings. And otherwise, if one of them is left, one is right, then the left remains, because that's an error of some kind. So we propagate the error. And only if we have both in the right, then we can apply the function f. So then we return the right of f of x1, x2. So it's obvious how to generalize this function to n arguments instead of 2. But the code would have been very complicated to write. We would have a lot of cases. So one solution would be to use a list of arguments and recurse over it in some way. And the second solution is to use curried arguments, which is going to lead us to the app method. So let's look at the first solution. So this map n1 takes a list of op A and returns an op of list A, because we don't have a function. Let's just instead of a function of n arguments, let's just put all these arguments into a list. So that would be sufficient. We can always add a function after that. So we can see how that works. If there's an empty list, we go into an empty list. And for a list having a head and tail, we do map2 with head, and then the rest we use mapN1 recursively. And the function that map2 uses is just appending x, which is the head, to the list t, which is in the tail, after we already did mapN1, so we have an op of list A. So t is list A. and x is an a. So that's working, but it's not very great. It's still quite clunky to use, because then we would have to have a function that takes a list of arguments. So using this in practice would be quite inconvenient. So let's try to see how we can do it better. And the starting point is to define a curried version of map2. Now, map2 takes 2 arguments like this, and the function f takes 2 arguments like this. Now, if we instead use the curried version, then the function f would have a type signature like this. So we would, instead of taking a tuple of a, b, we will take a and return a function that takes b and returns z. So that's equivalent, but it allows us to do an interesting thing. Namely, we have now a function from a to b to z, and instead of taking a pair of a, b and returning op z, we also curry that. So we take op a and return a function that takes op b and return op z. So that's clearly just a rewriting of map2 using a different API, a different type, which is equivalent to the previous type. So there's nothing new really, except for this curried function type instead of uncurried. Now, Fmap does not have this type signature, but here's a definition. Now, let's also introduce this syntax, which would be more convenient. Remember, in the short notation, we often use this kind of notation, where a function is fmapped over a container. So then we can just define that with this syntax. It's just to write this instead of that. So now, once we do that, let's apply fmap to f of this type. So why does fmap not give us this? Why do we need fmap2? That's the question. Well, fmap doesn't map this to this. What does it do? Fmap would take this, which is of the form a to something, and after fmapping we would have op of a to op of that something. So the type would be like this: op of a going to op of b to z. And that's not what we wanted to have over here. We wanted op of a going to op of b going to op of z. So that's why fmap doesn't work this way, and we need fmap2. So what is missing for fmap to be able to work this way? So what is missing in fmap that fmap2 does have? Well, clearly what is missing is to be able to transform this into this. So this is the transformation that fmap doesn't have, but fmap2 has. Somehow fmap2 already does this. Let's denote this transformation by app. So this is how we usually define app. So this is the transformation that, if added to fmap, would give us fmap2. Well, we can define this transformation for either just in the same way, more or less. It's a slightly less code to write, but basically the same code. Just there's one fewer argument because the function f isn't here. See, the function f would be in the Fmap. So by considering app, we have simplified our life. Fmap2 has two concerns. It takes this f, it needs to map A to B, and also, sorry, I'm looking at Fmap. Fmap2, it has two concerns. It needs to do this thing with two arguments, and also it needs to apply f. Whereas app only has one concern. It only disentangles the two arguments somehow. And f is handled by map. So let's define fmap2 through app and fmap now to see how that works. Now for convenience, let's define infix syntax for app, which would be this. It's just so that we can write fab star fa instead of app fab fa. So that's just syntax. It doesn't change what this function does. Now, with this syntax, which is defined here, we can now define fmap2 via app and fmap. So how do we do that? Well, we need to return this function. So we take op-A, take op-B. We need to return an op-Z. So let's first apply fmap to op-A. So f has this type signature. Applying fmap of f to op-A gives us op of B to Z, because f maps A to a function of type B to Z. So now suppose we had this x, so we could define it like this. Now we can use app on that x and transform that x into this. So app of x of op-B would be of type op-Z. So this would be app of this of op-B. Now if that's kind of clunky, but if we write it in this infix syntax, we write this instead of that, and we write this instead of that. So in the Scala syntax, these two operators will associate to the left, because the only way to associate to the right is to use the colon as the first character of the special syntax of the operator. So therefore we can simply write this instead of fmap of f of opa of app of and so on. So this syntax is that first we compute this, so it associates to the left. So it's as if we had parentheses around this, around fmap opa app opb. So, and this syntax is very similar to just as if we had been able to directly apply a function f. Notice this function has this type, as if we could apply it directly to opa and opb, although we can't because f needs an argument of type a, and this is an op of a, so it's a functor of a. So we can't directly apply f to opa. This would be incorrect in terms of types. So with these special separators, we can do it now. So here's how we can define fmap3. OPA, OPB, OPC going to this. Let's define Fmap4 like this. So now you see with this weird looking syntax, we can define Fmap3, Fmap4, and so on in a very easy way. And we can actually use that directly. We don't need to define Fmap4 and call it, because this code is so concise already. So let's see how we can just use directly these operations. Now, I just remind you that these operations are fmap and app. They're just written in infix syntax. There's nothing new about them. They're just fmap and app. So having these operations, let's have a little test and do the safe divide. So we divide by a number, but if that number is 0, we give an error message. So if it's not 0, we divide. So imagine we have a function of this type, double to double to double, because now we need curried functions. So now we can just write code like this. F safe divide to 1, safe divide for 2. And another test is we want to create a validated case class. So all we need to do is to have a curried class constructor. Now the ordinary class constructor would be uncurried. It would take a pair of arguments. What we need is to, so this would be C2 apply. So this is the ordinary class constructor with 2 arguments, and .curried is a standard method on a function in Scala. So this is in the standard library, and the result is a function of type double to C2, which is a constructor of the type C2, but it's curried. So now, since it's curried, we can just use like that. We can use it like that. So in this syntax, we don't need to call map2, for example, directly. We just write as if these are directly applicable. This is 2 divided by 1. This is 4 divided by 2. We could just implement safe divide as a syntax as well if we wanted to. And then we would have code that's maybe easier to read. In any case, now we can see that using the method app and in the syntax, so it's basically app, which is defined as this kind of function, it becomes easier to write code with applicative functors. So this app seems to be an important method that is simpler than fmap2 or map2. It allows us to define map3 and map4 and so on. And actually, it allows us to write code quicker without explicitly calling those fmap3, fmap4, and so on. So basically, what we have found is that fmap2 can be defined through app, if we have app, using this code. We just use fmapf, and then we apply app to the result. That was our code, essentially, that defined, first we do fmapf of this, and then we apply app to the result, to this. So that's what we just found. Now, can we also define app through Fmap too? Yes. And the way to do it is to set a, the type parameter a here, to be the function b to z. We are allowed to do that because these parameters are arbitrary. So we can just have a special case where a is equal to that. And then here we would have a type like this, b to z going to b to z. So we have an identity function of this type always. And we can just apply fmap2 to that identity function. And the result would be a function of type fa to fb to fz, but a is b to z. So the result will be of type like this. And so that's just fmap2 applied to the identity function of this type. Now, because we have defined the type parameter a through b and z, we have one fewer type parameter in app, only 2 type parameters in app, whereas in fmap2 we had 3 type parameters. So it is in this way that fmap2 is more complicated than app. So actually fmap2 and app are computationally equivalent. We can define fmap2 through app. We can define app through fmap2. And this diagram illustrates how that works. The type diagram starting from fa, go by fmap f lowercase f has this type. So f mapping it over fa gives you f of b to z. Now you app that, you get this function fb to fz. Or you can directly fmap2 from here to here, and that should be the same. And so clearly app is equal to something like fmap2 of identity, if this is identity. So if we take f to be identity, then this arrow is just identity arrow. So these are the same. And therefore then app is the same as fmap2 of identity. So this diagram shows you at once the two equations, the expressing of fmap2 through app and the expressing of app through fmap2. And similarly, we can define fmap3, fmap4, and so on. And here's a diagram for fmap3. It is slightly more complicated because we need to first map to this, then we need to do app with these type parameters, and then we need to do app on this argument. We need to keep this argument constant and app on this argument with parameters CZ. So in order to do that, we need to fmap. In other words, we need to lift app from its ordinary type, which is this, into this type, which is kind of a reader monad with this as the environment. So that is a reader functor fmap here. So this diagram shows how fmap3 is really defined, but in the code we don't need to worry about this because it's automatic, because we already query this argument. So we don't need to explicitly fmap when we use the infix syntax, which we have just seen in the code. I would like to call your attention to this pattern that we have seen before, that we have some kind of equivalence between two functions or two methods. And the equivalence works by taking Fmap and composing it with one of those methods. And usually one of those methods is a natural transformation and another is a kind of lifting. So we have seen this pattern several times before, where we were able to get two functions that are computationally equivalent, but one is simpler than the other, because there's this Fmap that one of these functions already does and the other doesn't. And so this function becomes simpler. It has fewer type parameters and fewer arguments. So let's recall the zip operation that we have seen before. And let's see how that operation is related to map2. To find that out, let's think about these two types. They are equivalent. Their equivalence is given by the curry and uncurry methods in the Scala standard library, as we have seen. So we can take this Fmap2 that we had in the previous slide, this Fmap2, and we can uncurry it. And if we uncurry it, we'll have a type signature like this, which is a tuple, and here's also a tuple. So now let's do the same trick we did in the previous slide when we substituted an identity function into this Fmap2 in order to obtain a simpler natural transformation. So in this case, the identity function will be of this type rather than what we had before. What we had before was this type, but we uncurry now. So instead of a function type, we'll have a tuple type, like this. So let's do that, and the result will be that we have Fmap2 with this. Now we take C, in other words, equal to the tuple A and B. So we set the type C to be the tuple AB, and then we have a function of this type, which is FA, FB going to FA to B, because C is tuple AB. Now this function is called zip because it's a very similar type signature to the standard function zip defined on sequences, where you take two lists, you zip them, and you obtain a list of pairs. So here F is the list type constructor. So then the zip function can be seen as taking two lists of maybe two different types, not necessarily, but maybe, and returning a list of pairs. So let's check that again. Zip and Fmap2 are computationally equivalent. So we define zip like this. Can we define Fmap2 via zip? Yes. All we need to do is we first need to do zip. That will give us this. And then we need to apply Fmap to F, which will take FAB into FC. So this is the type diagram that illustrates this. So we do a zip, we get that, and we apply Fmap F, and we get FC. Or we can go directly from here to here using Fmap2 of F, which is the uncurried version. So this diagram at once expresses the equivalence of the two equations here, because you can take this to be identity, this function, and when you do that, these two become identical, because Fmap of identity is identity by the functor law. Therefore, these two are identical, and so zip is equal to Fmap2 of that F of the identity. So that is this equation, and otherwise you get the second equation. So we can think now that applicative functors that were initially defined as something that has map2 could be equivalently defined as something that has zip. Of course, or something that has app. Those are also equivalent. And certainly laws should apply and hold, but we will look at laws very shortly. We could call a functor zippable if this zip function exists for it. And that would be actually weaker than applicative, as we will see. But there doesn't seem to be a good name that everybody uses for functors that just have the zip method and nothing else. There are type classes for that in different libraries. They're called differently. For example, in the cats library, it's called semigroupal. And in the Scala Z library, it's called apply or something like that. Notice also the same pattern, which is a natural transformation is computationally equivalent to a lifting. And this equivalence certainly needs to be demonstrated rigorously. We have not done this in this slide. Here I will also have not done this. We have indicated that they are defined through each other, but that's insufficient to show that they're computationally equivalent. You have to show that this is actually they're isomorphic. In other words, if you take app, define Fmap2 from it, and you take that Fmap2 and define a new app from it, then you have to show that that new app is the same as the app you started from. Similarly here, you would need to show that if you take a zip, say, and you define Fmap2 through it, and then you use that Fmap2 to define a new zip, then that new zip will be exactly the same as the old zip that you started with. And you have to also show that if you start from Fmap2 and go in the other direction, Fmap2, define zip, define the new Fmap2, and show it's equal to the old Fmap2. Now these proofs are very straightforward, and we have seen one of these proofs in a previous chapter in detail. So I'm not going to go through them again, especially since it's exactly the same pattern, where two functions are equivalent and they differ by applying a composition with Fmap F. So this is a pattern that we have seen time and time again, and so it's sufficient right now to recognize it and understand that the proof is exactly equivalent, analogous to the proof we have seen in chapter 7, I believe, where this was written out in full, this equivalence proof. Finally, we can also ask, are the operations app and zip equivalent? They seem to be two sides of the applicative coin. Indeed, they are. In order to figure that out, let's remember that we started app by setting A to B to C function. So let's do the same with zip. we will get this transformation. This is what zip does. Now, can we get an FC out of this? And if we do, then we will get an app, because app is basically this going to this going to FC. So we could just query this to get the correct type signature for app. If we could only convert this into an FC. Now, obviously, we can convert this to FC because this is a function from B to C and we have a B. So we can clearly just apply this function to this B and get a C. Let's call that function eval, which is this function. And then fmap of eval will be a function of this type. It is trivial to define that function. Then we just do fmap of it, and we get this. So then we transform from here to here. And we just uncurry. Now, we get an app. I write it with two P's, just so that it's different name from app. But this is just the uncurried version of app. So the uncurried version of app is equal to zip composed with fmap of eval. So we see again exactly the same pattern, that app is a zip with some fmap, although this is not an arbitrary function, it's a specific function, but it's a very similar pattern, and so it suggests computational equivalence. So let's try to define in the other direction how to define zip through app. Well, that's done like that. So app needs functions that operate on two different types instead of zip. Let's prepare for this. We would need a function that makes a pair out of two elements. So let's call this function pair. And fmap of pair, let's just denote fmap like this for brevity, which I have already done in previous chapters. Seems to be a good notation. And then clearly we get this kind of situation if we apply this fmap of pair to some fa of type f of a, then we get this. And that is something that now resembles what app likes to take as an argument. So then let's see, zip of two different values of a and fb would be equal to app applied to a pair. So app has this type signature. We need to give it a product. fb to c is this, where c is a to b, and this is fb. So then, applying that app, we get fc, and c is a to b. So that's exactly the right type, namely f of a times b. So c is a times b, not a to b, sorry. C is a times b. And so we have expressed zip through app, and we have expressed app through zip. And here's the type diagram. We need to take care about what types we're using. So that's why I have written out all these types in full here, the type parameters for app, for example. You see, app is defined like this, but now we need to use as its first type parameter, we need to use actually B to C. So actually, no, that is a mistake, sorry. This needs to be deleted. This is not app B to CB, this is app BC, because this is how I defined it. So this is just app BC. I will correct this slide. So we start with this type, we do a zip on it, we get this, and then we do fmap of eval, and then we get fc. Or we start with this type, we do an app on it, which is going to give us fc directly. So I need to delete these two symbols and then and also these two symbols, and then this diagram will be correct, and these type parameters are correct. So clearly we can also do this with curried arguments. We just need to define curried versions of zip, which is like this, and then we have exactly the same relationship between app and fzip. So I just call this fzip where it's curried, and then fzip pq is that, and it's exactly the same, except we don't need to do the tupling of arguments. We just need to give the arguments one by one. And now we see that this function takes this argument, and this function also takes that argument. And so we can carry that away. We can omit the argument q, and we can write it like this. Which is nice because it allows you to reason quicker about what is equal to what. You would have to write fewer symbols. You see, we can also omit the argument p, because this is now app of pair of p, which is first you apply pair and then you apply app in my notation. As function composition in my notation goes left to right. And here are the explicit type parameters that you need for this to work. So having looked at all this, we still don't know what the laws are. Now we have map2, we have app, and we have zip. Let's now derive the laws for these methods. The motivation for laws comes from our initial idea that map2 is basically a replacement for a monadic block or a functor block with independent effects. And in other words, map2 with two arguments and a third argument, which is a function, replaces the functor block of this kind. So we started with this. We expect, therefore, that whatever laws of the monad hold for this kind of construction should also hold for map2. Therefore, we just will take monad laws, which we considered in the previous chapter, and write them, replacing the functor block with map2 where we can. So the first two laws we consider are naturality laws, and they come from manipulating data in one of the containers. So, for example, we can manipulate first in this container, and that should be the same as if we acted with the function f on x, like this. So if we rewrite that in terms of map2, and we get on the left, we get this map2 of this and of g. On the right, we have map2 of this and a modified g, which takes x and y and returns this. And similarly, if we apply map on cont2 instead of cont1, we will get the right naturality law, which is like this. Very similar, except acting on y instead of acting on x here. Also, the monads have identity laws and associativity laws. So let's look at those. The associativity law is that we can inline the generators in a for yield block or a functor block that is on the right hand side, and that should be the same as when we write all of these in a single flat for yield block. And we can inline in two different ways, and that should be the same. So that's the associativity law for the monad. Now, if we rewrite that, so the idea is that we have three containers, and we have a function of 3 arguments, let's say. And then we first go over the first container, and then yz go over the second container. Now we need to do this rewriting because we need to formulate everything in terms of for yield blocks with just 2 lines, because that's map2. And for yields blocks that don't depend on containers don't depend on on previous values. So this is a map2, and then this is also a map2. So we have a map2 of cont1 and map2 of cont2, cont3, and then the function that just takes 2 arguments puts them into the tuple. That's the Scala syntax for that. And then the function that takes x and yz and returns g of x, yz. So we need to untuple like this, because the result of map2 will be a tuple. On the right, we first apply the for yield block to container 1 and 2, and so this becomes map2 of cont1, cont2 with the tupling function. And then we do map2 of this and cont3 with this function, which now has to untuple xy first. So therefore, this is the associativity law for map2. Let's consider the identity laws. Identity laws express the relationship between map2 and the pure method. So it appears that applicative functors also need the pure method. It's very useful to demand that the pure method exists and satisfies identity laws. Turns out that this constrains applicative functors in an interesting way, a useful way. Without identity laws, there are just too many ways in which you can define map2, satisfying just the associativity law. So the identity laws are that if you do a pure on the right hand side, that's the same as if you just had x equal to a, because that's an empty context or empty effect. So then we have the left and the right identity laws, because the pure or the empty context can precede a generator, or it can follow a generator. So in both of these cases, we have this equivalence, and so these two laws are written like that. So for example, here is map2 of pure A and the container, and then their function G. And on the right is just a simple container map with this function that substitutes A instead of X. And similarly, the right identity law. So now let's derive the laws for zip. The reason we want to do it right away is that these laws are quite complicated. So these are very complicated combinations. They're all kinds of things that are complicated. So basically, map2 of cont1, map2 of cont2, cont3, that is simple. So you just change the order in which you apply map2. But everything else is just some kind of bookkeeping that we should be able to get rid of and simplify somehow. So, for example, we don't want to talk about arbitrary function g in the law. We'd like to simplify that so that the law doesn't contain arbitrary functions. So we have seen before that this kind of simplification can be obtained if you, instead of liftings, you consider natural transformations. And so that's computational equivalent, but the laws are much simpler. We have seen that before. That's, for example, the laws for flatten in the monad are much simpler than the law for flat map, the laws for flat map. So it's the same thing will happen here, and it's reasonable to expect that this will happen. So let's do that and derive the laws for zip. So what are the naturality laws? Now, naturality laws are written like this, and we here need to deal with this kind of function, where we modify the function by taking some arguments and so on. Now, it's not very nice to reason about such functions, so I would like to introduce a short notation for that. The source of difficulty, or the source of lack of elegance, is that we need to write these arguments, and then all we do is we put these arguments right back into the function g, except one of them gets modified. So what if we need to modify both? So that's something we would like to be able to write more concisely. And so that's why I introduce this notation. So first I introduce this function product notation, which is a function on a product defined like this. So this is just syntax, so to speak. And this function is trivial and doesn't really do very much. But using this notation now, we can do a lot of interesting things. For example, we can now rewrite the laws from map2 like this. Fmap2 is just map2 where the first argument is the function with this type, and the second argument is a tuple, is a pair. Where, just swap the arguments as compared to map2. Now, this is the short notation for first container dot map f, if you see that. Then it's a map2 with this tuple, so we write that as a product like this. And on the right hand side, it's a map2 of that tuple unmodified, but the function g is modified in that the first argument gets acted upon by function f. And this is expressed like this in the short notation. So we have a function composition on tuple. So this is a function that acts on a tuple AB. And this function applies f to A and identity to B. So that's a function that takes a tuple AB and returns a tuple f of A, B. And then we apply g to that. Therefore, we get g of f of A, B. That's precisely what we have here. And so, therefore, this notation can be used somewhat shorter than the code and easier to reason about. So these are the two laws that we have so far for naturality. This is the associativity law, where I just have this notation G 1, 2, 3, G 1, 2, 3, to indicate that this is just the function G with 3 arguments, but the second and third arguments are in a tuple. And here the first and second arguments are in a tuple. So I have just rewritten the associativity law in a short notation. It's slightly shorter than this, but it's still quite ugly. And finally, the two identity laws, which I rewrite like this. Pure, acting on A, and then tuple with Q, and then this function, and so on. So that's exactly the law here. And then I write y goes to g of ay, as b goes to g of ab. So these are the laws for map2. So let's express Fmap2 through zip. Well, we can express it certainly like that. Written out with all the arguments in full, it's like this: Fmap2 acting on G and also acting on this tuple is zip followed by lifted G, or Fmap of G, acting on this tuple. And so since this tuple is the same, we can omit that argument in the curried equation, where both sides of this equation are now functions acting on the tuple Q1, Q2. So this is how we can express Fmap through zip, and we can substitute this Fmap into the laws, and then we will obtain the laws for zip. To simplify things, we can combine the two naturality laws into one, where we use two functions, f and g, or f1 and f2, acting on q. So that's how we could rewrite these laws. And naturality then follows for zip, because Fmap G is zip followed by lifted G. So we can just write it here. And the right-hand side of the naturality law is zip of this followed by lifted G. So now you see we have this followed by lifted g equal to this followed by lifted g, and g is an arbitrary function. So clearly we can just substitute g to be identity and get rid of it. So that's therefore the naturality law for zip. And if this law holds, we can add an arbitrary function like this, and we restore this law. So therefore, the naturality law for zip is equivalent to the naturality law for Fmap2. So what does this naturality law say? It says we can first transform both arguments of the tuple using some functions, and then we can zip them, or we can first zip and then we can transform both arguments of the tuple using some functions. That's a typical form of the naturality law that says you can Fmap something before your natural transformation, or you can Fmap it after natural transformation. The results are the same. Let's look at the associativity law. It's more complex. But if we do this substitution, so we take the law as written here, and we just substitute Fmap g as zip followed by lifted g everywhere. So the result is that we have g of a zip and so on equals that. So the arbitrary function g has a different set of arguments on the left and on the right. Now you see this g1, 2, 3 was actually this kind of function, where we first untuple 1 and 2, and then we have 3. Or we have first we untuple 2 and 3, and then we have 1. So this is what I am indicating in this very informal notation. I don't want to write a lot of parentheses and so on. I just want to indicate what we want. So this is just shorthand for that kind of function and that kind of function. But if we substitute zip followed by g here, so then we'll have zip followed by g, which means that we actually need to substitute the full term, zip followed by g on the q. So zip on that followed by g. That's how I've rewritten it here. Now these these tuple transformations all come from this isomorphism, which is trivial. It's just we can untuple this or we can untuple that. They're equivalent. So let's not have to let's not write all of this explicitly every time that we are untupling and so on. Let's just do it when needed. Whenever we have a tuple of a tuple like this, we just untuple and rearrange as required. And this operation I want to denote by a special symbol. And so this is the symbol, which is kind of equivalence. It's not precisely equal, but it's equivalent up to this trivial isomorphism. So in other words, very simple isomorphism that doesn't require a lot of work. And so if we get rid of that, then the g is an arbitrary function. So let's substitute identity instead of g. And the result is this law. So we first do a zip on Q1 and a zip of Q2, Q3, or you first do a zip on Q2, Q1, Q2, and then a zip of that and Q3. And these should be equivalent up to rearranging the tuples like this, because the types are going to be different. So let's look at the type diagram to see what types there are. This type diagram is quite large, and so let's look at it in this way. So it starts from these three, FA, FB, FC, which I have put into the diagram in this order just arbitrarily. It doesn't really matter. Now, the first thing we do is we make tuples, say, of FA and FB. That is indicated by these two arrows. So this is just to make a tuple out of these two. Also, we make a tuple of B and C here. Then we apply zip to FA, FB. We get FAB. We apply zip to FB, FC. We get FBC. Now we can make a tuple from this and this. We get this tuple. We make a tuple from this and this. We get this tuple. Now we apply zip again to this tuple. So this gives us f of that. And this, after applying zip, gives us f of that. Now, actually, they are equivalent to some f of this because of this isomorphism. So this corresponds to that, and this corresponds to that. So this is the associativity law for zip. Its identity laws have complicated form, in particular because we have this arbitrary value a. And actually, we can simplify them if we replace this pure method by an equivalent method that doesn't have an arbitrary value a, which is an interesting trick, actually. So let me explain this simplification in some more detail, because this is a kind of a complicated law. We want to simplify it. So here's how we simplify it. Let's consider pure of unit. Just apply pure to the value of type unit. There's only one value of type unit. Let's apply. We get a value of type f of unit. So I called it WU because it's a wrapped unit. It's a unit that's wrapped in the type constructor f in some way. So with empty effect. So it's an empty value unit wrapped in an empty effect. So that's why I called it wrapped unit. Now it's a pure of 1. So in order to restore the pure function, all we need to do is to map this 1 into a inside the container f. So that is what we need to do. So in order to express pure through wrapped unit. So these are equivalent. You can see that if we use wrapped unit instead of pure, then things are actually simplified. And this is how we do it. So let's substitute first. Instead of pure a, we substitute this. Now, this we rewrite using this notation because the argument b is unchanged, and instead of 1 we have argument a. So we call G on this. So you see, so this actually is equal to that now, because we can pull out of zip, we can pull out this function using left naturality, and then we get zip of WU cross Q, where this now is outside the zip. It needs to act on the first argument, and so this is how I express that this function needs to act on the first argument of a tuple. The second argument of a tuple is unchanged. So now it looks like we have a lot of this bookkeeping where we just put units and so on. So let's denote these things temporarily, just so that we can reason about that a little shorter. So phi is this function, and beta A is this function. So this is a trivial kind of code that just adds unit, and this code just takes a tuple of unit and B and returns a tuple of A and B given a fixed value A. So it just substitutes A instead of unit, and the B is unchanged. So this identity function is acting on B, and this function is acting on unit, and this product, this function product, gives me a function of this type. So now this function is a composition of this kind, because we first take a B, we apply phi to it, which gives us 1B, so 1 times B. Then we apply beta A to it, which gives us A times B. And then we apply G to it. So that's exactly what's happening here. If we use that, the advantage is that these are function compositions, and we can reason very easily about function compositions. So if we substitute into that naturality law, which we just had in this form, then it becomes G, so this is beta A. This is actually beta A by definition, so G, beta A, zip. Now, clearly, beta A can be composed with G and then lifted, because that's just a functor law that we can lift after composition. And then the right-hand side of the naturality, of the identity law, is like this, which is what we simplified here as this composition. Therefore, the naturality law, the identity law becomes this equals that. But here we can also put phi inside, so we can lift phi first, and that would act on Q first. So now we have an equality that has a common prefix of some functions. We can omit it, and the law becomes much simpler. It's like this. So now phi is this isomorphism between B and the tuple of unit and B. Again, this is a kind of a trivial isomorphism that we can apply whenever needed. we don't want to keep writing phi all over the place. Phi lifted to f is the isomorphism between these two. Again, let's imagine that it is applied whenever necessary. We will express that using the symbol that these are not really equal, but they're equivalent up to applying these isomorphisms whenever necessary. So the left identity law therefore can be rewritten like this, and the right identity law similarly like this. So then let's actually simplify the notation some more. Instead of zip of PQ, let's write this. Now this is just a symbol I invented. It doesn't matter what it is, but it's kind of a zipper symbol. If we write it like this, then associativity and identity law look like that. Now these laws are basically laws of a monoid up to different types that I did not write. So this is of type Fa, this is of type Fb, this is of type Fc, and assumed transformations that are isomorphisms here and here. Naturality law is written like this. So you can lift F, act it on Q1, lift F2, act it on Q2. It's the same as if you lifted this and acting it on the zip. Now the wrapped unit has no laws at all. It's just a fixed value of type F1, F of unit. The naturality law for pure will follow automatically from the definition of pure through the wrapped unit. This is, again, the pattern we have seen, where one equivalent method is simpler than another, and it is equivalent nevertheless, and the other method is expressed through the first method using some Fmap. So that's very similar pattern. And so actually we see that the laws of applicative have become extremely simple and suggestive. They're very similar to the laws of a monoid. There's associativity and two identity laws. Now this syntax, of course, is just zip, right? So this is p zip q. In Scala you can write zip in an infix notation already. So you can just say q1 zip q2 zip q3, and you don't have to worry about parentheses. That's the essence of the associativity law. And the identity laws mean that you can have something that you zip with and it doesn't change that thing you're zipping with, up to an isomorphism, of course. They're not actually equal. They're isomorphic. They're equal when you apply those isomorphic transformations in the right places. So obviously this is much simpler than the laws when formulated in terms of map2. I already discussed in a previous tutorial that naturality usually follows from parametricity in code that has type parameters. So when we want to check laws for specific functors, then we don't usually need to check naturality. It will be obvious. If our code is fully parametric and generic in all type parameters, then naturality will be automatic. Associativity, of course, needs to be checked, and identity laws need to be checked. So actually, it's interesting that we have not seen the third naturality law for map2. We have seen two naturality laws, and we have derived naturality laws for zip. But actually, when we define map2 through zip, there's one more law, one more naturality law, which we will see shortly. And now it became obvious that we were missing a law. So our consideration when we derived the laws, they gave us two laws, but they didn't give us all the laws. We could have been more clever right here, but we weren't. However, once we understood how to formulate the laws in the best way, then obviously the right thing to do is to start with these laws and then derive the laws for map2 from those. This also gives us assurance that we haven't missed any laws. This is a very common construction, a monoid. And generally, this idea of having associativity laws and identity laws is a very common pattern that happens time and again. And once we see that, we have assurance that the laws are complete. This is the complete set of laws for an applicative functor. If we formulate the laws in terms of zip and wrapped unit. So we have now great assurance that we are on the right path. We have found the correct laws for the applicative functors. Now, functors that are zippable, as I said before, they do not have pure necessarily. They do not have wrapped unit. They only have the associativity and naturality laws. But applicative functors must have both this and these laws. So as I started from monads, well, clearly if a functor is a monad, then it will satisfy all these laws too. If we define map2 through the monad construction, then we will automatically satisfy all applicative laws, since those laws were motivated from monadic laws. But there are some applicative functors that cannot be monads, and so actually all monadic functors are applicative, but not vice versa. This is actually a mistake. It's a strict superset. So there are strictly more applicative functors than monads. And another way in which applicative functors are a superset is that applicative functor implementation may disagree with the monad implementation of the function map2. In other words, we may want to define map2 and zip and so on in a different way for a functor that already has a monad implementation. But for some purposes, we might want to define it in a different way. And we have already seen that in the first part of this tutorial, when a monad would, for example, for the either functor, the monad implementation would take only the first error in the computation, and we want to gather all errors. So we define an applicative functor differently so that it collects all errors. So that definition disagrees with the definition of map2 that would follow from the monad. So strictly speaking, we should rename this functor into some other name just to distinguish it so that we don't get confused, because we might want to write applicative code in a monadic for yield block and then we would accidentally have the wrong implementation of map2. So strictly speaking, we should avoid defining map2 at the same time as a flat map so that they disagree. But in practice, this does not happen very often. But this is another way in which applicative functors are a strict superset. So sorry about this mistake. It's a superset. So what is the third naturality law? It's a law where we transform the result of map2. We have not done this. We have not thought of doing this. Transforming the result of map2 should be equivalent to doing map2 like this and transforming the result of G. So when we write it in terms of map2, we get this equivalence. And if we write it in the short notation, then map2 of G followed by some lifted function must be map2 of G on which we act with that function. Or if we rewrite the same thing by substituting explicitly the arguments P and Q, which are here cont1 and cont2, then we get this. Now, this law follows automatically if we define map2 through zip, because that's the definition. Fmap2 of G is this. But then clearly, if we apply some function f to the result, then it's the same as if we lifted the composition of G and f, because this is the functor composition law. So this is a very obvious property then, that this naturality with respect to transformation of the result of the map. So we could have noticed that we're missing a naturality law for map2. If we looked at map2 type signature, we see it has 3 type parameters. And usually there is a naturality law for each type parameter, because naturality law means we aren't we aren't changing the results of any transformations applied to a certain type. And for each type parameter, we can transform that value of that type separately from transforming values of all other type parameters. And so zip has 2 naturality laws because it has 2 type parameters. But map2 has 3 type parameters, so it should have 3 naturality laws. So that's the third naturality law. Now, I would like to go a little deeper in analyzing what the properties of app turn out to be. So that's a very interesting direction, because it will show us more deeply what are the properties of app and what are the laws of app. Now, the laws of app are not so easy to derive, and we will have to prepare ourselves for that. So app is a function of this type. Now, we can consider it as a kind of lifting. So we have this function and we lift it into this. But actually, this is not a function. This is a type constructor whose type parameter is a function type. So this is not really a lifting of a function into some other functor. But we can think about it like this. We can think, well, this is just like a function a to b, except it's a little twisted. So it's kind of a lifting from a twisted function type into the function of a type constructor to type constructor type. Now, a lifting should have identity and composition laws. just like lifting of a functor would have type signature lifting from Fmap going like this, AB to FAFB. So that is a classic lifting, where we get our intuition about lifting. Now lifting in the functor case has identity and composition laws. So just two laws, which means that if we lift identity, we get identity, and if we lift composition of two functions, we get a composition of two functions. So that's very reasonable. Can we find the same laws for this lifting? Can we find identity and composition laws for it? Now, if we could, then we would first of all need a value of this type, FA to A, which would represent the identity for this lifting. And then we would demand that the function app takes that identity value and returns an identity transformation on FA. So how do we get a value of this type? Well, let's call it by this symbol, identity with this dot in a circle. Well, we have a pure method on an applicative functor, so we can easily create an identity transformation like this and put it into pure, and that would be a functor type value with empty effect, because we're pure, we're using pure, and identity transformation. So that looks like a good candidate for a kind of value that should not transform anything. We will see that this is indeed the case. Now, the second question is, how do we check the composition law? Well, in the usual functor lifting, it's clear what the composition is of two functions, a to b, b to c. They compose and they get a function a to c. And similarly here, you compose fa to fb, fb to fc, and you get fa to fc. So here we have this type, however. So how do we compose this and this so that the result is this? Well, it is not easy to do that necessarily, but let's try to use map2 to implement that composition. Can we maybe do that? Because we almost have what we need with map2. Or we could use zip. Maybe zip is actually even easier to visualize here. If we zip this and this, we get an F with a product, AB and BC. And we can just compose those things in a product and Fmap. So that's what the Fmap2 gives us in one go. It takes two functions, P and Q. Now, let's denote by the symbol this kind of twisted composition where we compose this with this and yield that. So we will define it now using this code, which is fmap of gh, fmap2 of gh, where the function takes a to b and b to c and returns just the composition of these two, p compose q, p and then q. Now, it seems that we have defined a reasonable candidate for identity and a reasonable candidate for composition. Let's check the laws. What are the laws? Well, it turns out they are precisely the laws of identity and composition, namely these. The composition of this identity with something does not change that something, and composition is associative. Also, there are two naturality laws, which basically say that Fmap, or lifting, plays well with this composition. If you lift first and then you compose, or you can first compose and then lift this and act on the result, and so on. So you can check that these types make sense. The first three laws are actually the identity and associativity laws of a category, where the morphism type is this twisted function type, the identity is this, and the composition is that. I remind you that the category laws are identity and composition laws. So you need to have just these laws, associativity of composition and identity laws. The last two laws are naturality laws. They're connecting this twisted category composition with the ordinary Fmap, which is the ordinary lifting that the F must already have, because F must already be a functor. So these are the 5 laws that are very interesting because they show that app is actually kind of a lifting. It satisfies functor laws as if we had a functor between these two categories. So in this way, we have justified calling app a lifting. It's like a Fmap function, except the category has a twisted type. This is another way in which we have assurance that our set of laws for the applicative functor is reasonable. It is not too large, not too small, because this is just a category law in some suitably defined category. In other words, in a category of functions with this type. Morphisms of the category have this type. I remind you what I call categories just morphisms where this arrow is just a general symbol and you have to define what it is in any particular category. And then you need identity laws and composition laws, which are these. So having defined that, let's check that this is actually true. I haven't actually derived that these laws must hold. They follow from the mapN laws. So I will now go through this derivation. For example, let's start with the identity laws. So let's consider this. We substitute the definition of the product, of the composition, which was here. And also, we need to look at slide 7, because that defines laws for the Fmap. So if we substitute that, we get Fmap2 of this, which is just that definition here. But we are working on pure of identity function. So according to the law on slide 7, this is equal to that. So we have Fmap2 of something and pure. So that's supposed to be equal to this. So let's just copy this over and we get that. But now you see identity function followed by b is just b. So now we have b going to b, which is an identity function. We lift that, it's still an identity function. So that's equal to h. So that's why the identity law holds. Similarly, we derive the right identity law. Associativity law, we also need to substitute. Then, according to the third naturality law, now this I'm just using a very short notation where this is a function that takes two arguments and returns the composition of these two arguments as functions, because that's what I want to use here. This is this function. This, I just denote this by that, this symbol. Now we use the third naturality law and move the function, this function, out of Fmap2. So then Fmap2 with this function hk is equal to this function lifted of Fmap2 of identity hk. So that's the third naturality law. And once we do that, we can just see that whenever we have the category composition, it's just basically Fmap of this composition function. And so then every time you have this, you have a composition. So then you basically have Fmap2 of these, and this is mapped to that, and that is mapped to that. But this is basically the same as the formulation of associativity law for Fmap2, where we had to use these functions that rearrange the tuples. Now this function is the same. This is the g in the Fmap2 law here. This is the g. And these are precisely the right-hand sides and the left-hand sides of this law. This is that and that, precisely that law. And so, because Fmap2 has that associativity law, this must be equal to that. So we find that these are equivalent. So associativity law for Fmap2 is equivalent to associativity law for this. The naturality laws can be derived by writing out again what is the naturality law for Map2. We have now 3 naturality laws for Map2. So, for example, you do this, you act with something on G. We write a definition of the category composition. There's no name for this category, by the way. I don't think there is. But I just think about it as the category that allows me to think of applicative functors as having a lifting somehow. It's just a category where this is the composition. So this becomes my left-hand side, and then I can transform it. So just put this outside, put this function outside. So I get that, put it in here, and I have GH. Then I put that is the what is this? Let's see. Fmap2 of this. All right, I have another naturality, right, where I act with some function on the G. So that's the third naturality. So I can pull this out of Fmap2, which is this part. I pull it out with, and the result is that I have just xy going to x and then y, which is this. So then I pull this out, and this is a definition of G O dot H. So then I have my naturality law for G O dot H, and similarly the other naturality law. So now the laws for app, let's write them out. So app has this type and it's defined like this. Identity law is that app of identity is identity. Right? So the laws for app are just the laws of lifting. We say that lifted identity must become identity, and lifted composition must become composition. So these are the laws for app. Identity law, let's derive it. Well, we can derive it in a pedestrian way. And let's do it first. So app of identity applied to some Q. So what is that? So let's write the definition. So it's Fmap of identity, and then this is a definition of this symbol applied to Q. So let's write it all out. We have this Fmap2 of this function. Now, identity of this type is actually this function, if you think about it. But we uncurried it, so we need to uncurry because we want Fmap2, which is uncurried. You see here I have this Fmap subscript 2, which is curried, and Fmap without subscript is uncurried. Applied to a product of fx is just this. This is equivalent to this identity. And now I'm going to just simplify this by using the identity law from Fmap2, which is going to give me this. If I substitute the identity law for Fmap2, which is this, and therefore I have this code. Now identity of x is just x. We have x to x lifted, still identity. The result is q. Now there's an easier derivation, which I would like to use now because it's interesting and simpler. Consider these isomorphisms. They are obvious. They are not the same, obviously, because this is a value and this is not yet evaluated. You have to give it an argument and so on, but they are equivalent computationally. And then this app becomes basically, after this equivalence, if you look at this app, it basically becomes a categorical composition of Q and P. So Q has this type. You cannot do categorical composition unless both have function types. But because of our isomorphisms, we can replace A by 1 to A here, and so we do that. This must have been a double arrow. I will correct the slide. So Q F1 to B can be composed with P Fb to Z, and you get something of type F of 1 to Z, which is equivalent to Fz. So that's Fz. So that's, in this way, we can equivalently rewrite app as just this categorical composition. And then everything becomes just very easy, because then app of identity on Q is Q composed with categorical identity, and that's just Q by categorical laws. So composition law, again, very easy. If we say app PQ is just QP, and we just rewrite that as QGH, and then this is rewritten as app of H of app of G of Q, which is app of H QG QGH. Now these are equivalent because of associativity law. So in other words, once we establish the category laws, app becomes a lawful lifting. And all the other laws follow. So it's sufficient to establish the category laws, or it's sufficient to establish the zip laws, and everything else follows. So these are the all the possible ways of looking at the laws for applicative functors. So you can choose the one you like best, and different ones have different utility. For instance, the category laws are not directly so useful for coding, and they're not so easy to check, perhaps, because you need this complicated categorical composition and all these type parameters. So basically you have 3 type parameters in this composition, which is harder to check than zip that has 2 type parameters. But it allows us to look at those things in a very general way, which we will see later. So now I will go on to define various constructions that you can use to make applicative functors out of other types. We have seen in the previous chapter a large number of constructions for monads. Since all monads are applicative, all those monadic constructions also hold, but sometimes they hold for a weaker condition. In other words, not as in monadic construction that, for example, this was also a monadic construction, but it requires both of them to be monads. But now we only require them to be applicatives. Applicatives is a superset of monads. So this is a similar construction, but it is a superset, and so on. So we will now go through these constructions and show that the laws of the applicatives hold for each of them, assuming that the laws hold for the parts out of which you build